We're going to continue control dependence handling today, and hopefully we're going to finish it. This is another fascinating topic that has fascinated many people over the years, over decades, branch prediction. How do you figure out which way a branch goes without knowing, before knowing it, of course, or maybe hundreds of cycles before the branch is executed. So we'll see what techniques people have developed for that. But before that, your reminders, homework 2. Hopefully all of you are done with it. Let's do it today, right? Are you all done with it? Mostly? Or good. I see a lot of nodding heads. That's good, actually. And homework 3 will be out later today. And I've already given you one homework question. Maybe you predicted it and started it, right? You've done some speculative execution. How do you implement repeat moves in microprogrammed LC3B? There are pipelining questions, delay slots, interlocking, and maybe more. So everything we've covered before. And lab assignment 2 is due this Friday. That's not next Friday. That's what happens if you, this is a copy-paste error, right? So it's February 15th. If you haven't started yet, definitely get started. And if you haven't started yet, it's actually late. So you should do it very, very quickly. How many of you are done? It's good. I see at least one hand. That's the spirit. OK, and there's an extra credit portion, too. OK, these are the readings that I've been showing you in the last lecture. Hopefully, you're doing them. This reading will be especially relevant in the next 2 lectures, where we will cover out-of-order execution and control flow exception. Well, exceptions in general, how to handle exceptional conditions and recovery in the pipeline. So this reading will put everything together, hopefully. And you know that this is another reading that I will assign. And there's a talk tomorrow by the author of that reading, one of the designers of the Alpha 21264 microprocessor, which was one of the fastest processors of its time. And I would encourage you to attend that talk. It's not going to be about that processor. That processor is now about 16 or 17 years old. It's about a newer project that Rich Kessler is working on, which is the CPUs for the Cavium architecture. I believe they call it the Octeon. And I do not know the architecture. Actually, I looked at it, but he will tell you about it to all of us. OK. So last lecture, we've covered a lot of control dependence handling, but we haven't finished it. So we're going to continue with it today, especially focusing on branch prediction, which is one form of control dependence handling. And we're going to wrap up with other forms of control dependence handling. We're going to hopefully finish all of what I have. So just to warm you up, these are the branch types we were considering, some of the branch types that exist in most ISAs. You have calls, returns, indirect branches, unconditional branches. But we were focusing mainly on conditional branches for now, where the number of possible next fetch addresses is 2. When the fetch address is actually resolved, or branch is actually resolved at the execution stage, because you don't know the condition until then, right? So some of the potential solutions, if you remember this slide, which I've shown you several times, there are at least 6 different potential solutions. And we've covered 4 of them in some detail. Stalling the pipeline, we figured out it's not a good solution. Employing delayed branching, we figured out it's not a good solution. Do something else, we figured that it's a good solution with trade-offs, right? So you should know all the trade-offs, all of these. By the way, when I say it's not a good solution in the general purpose sense. So if you have a very specialized design, maybe stalling the pipeline is a good solution, right? Maybe. That may be the trade-off you make, depending on your design point again. But in a general purpose sense, stalling the pipeline wastes energy and wastes performance. OK, do something else. Eliminate control flow instructions. We've covered predicated execution. And we've covered predicate combining also, which is an optimization that the programmer and the compiler can do to get rid of unnecessary control flow instructions. And we're going to get back to predicated execution after we cover branch prediction, because there are actually ways to use predicated execution even after you have branch prediction. OK, you can also fetch. We haven't covered the guess the next fetch address. We've covered primitive forms of it, like always not taken, right? You're actually guessing the next instruction is always the next sequential instruction. And we've started on covering how to fetch how to predict the next target address, right? The target address of a branch. And we're going to cover multipath execution also briefly. So let's take a look at this guess the next fetch address solution, branch prediction. When you fetch the instruction, what is the next fetch address? We're going to guess that. Well, what is the problem? Let's review it again. This requires three things to be predicted at the fetch stage, right? One is whether the fetched instruction is a branch. Second is the direction of the branch. Remember, we're concerning ourselves with conditional branches only. And the target address of the branch. And we've covered that target address is relatively easy to predict or memorize if you have a conditional branch instruction where the target address doesn't change across different instances of the same static branch instruction at the same program counter. Right? In that case, the first time you execute the branch, memorize it in some hardware structure. That's the idea. That's the idea of the branch target buffer or branch target address cache. So you can hear these terms. Sometimes you hear target address buffer also, I believe. But the basic idea is you cache the target address of a branch when you first execute the branch. So the next time you see it, the hope is that that target address is in the cache. So how do you do the prediction of a target address with a branch target buffer? When you have a program counter, this program counter specifies the instruction you're fetching. You index the structure, which is a cache of target addresses. And if that program counter has stored a target address over there, this structure returns a hit and the target address, of course. Otherwise, it returns a miss and the target address. Concurrently, you do a direction prediction. And this direction prediction doesn't need to be in hardware. Right? It could be always not taken, for example. I should probably put a bubble over here that says somehow magically you get a direction prediction. It could be software. It could be hardware. It could be hard-coded. But let's say that direction prediction tells you whether or not it's taken or not taken. If the direction prediction is taken, and if the cache of target addresses provides a hit, that means that you'd better use the target address, at least that's what the predictor tells you, as the next fetch address. So this mux selects the target address as the next fetch address. Otherwise, you select program counter plus instruction size. Right? So that's the branch prediction. That's a nice branch predictor of a modern processor. This will become much more complicated as we get through this lecture. OK, everything clear so far? So we were almost here. And you remember we've done the calculations. If you actually do this for always taken. Now you can do always taken prediction, right? Because you've actually cached the target address. You can get the target address in the same cycle you're fetching the branch instruction. Because you can do always taken prediction, now you can reduce the cycles per instruction because we've discussed that most of the branches are actually taken. Most programs have loops that iterate a lot in them. And that's the reason why most branches are taken. OK? So how do you do this direction prediction? Now we know how to do this target address prediction. And implicitly, so we've solved two problems actually with this cache of target addresses. We've solved the branch target address prediction problem for conditional branches. And we've solved whether the fetch instruction is a branch problem. Because if you're hitting in the structure, if the program counter hits in the structure, that instruction must be a branch, right? Because you've inserted target address for that in that branch target buffer. OK. So what is the third problem? The third problem is how do you predict the direction? And that's the hardest problem, actually. So we're going to look at many different schemes, compile time and runtime. Actually, let me make it more sophisticated, because we're going to look at the more sophisticated schemes also. Now let's start with the compile time. Compile time schemes are static, meaning the hardware doesn't have a predictor in it. It uses a hint. Or it uses no hint in these cases that comes from software or that's built into the hardware. So let's take a look at the first two. These are easy, right? These are the easy cases. Always not taken prediction. Whenever you get to a branch, it's always not taken. You don't even need a branch target buffer in this case, right? And no direction prediction is needed. I guess that's not a direction predictor in that sense, but it's technically a direction predictor, right? You're predicting the direction that's not taken. Low accuracy, and we've discussed why that is. And we've also discussed that actually compiler can try to optimize this prediction, right? Compiler can try to lay out the code such that the not taken path is the likely path, if the compiler can figure out if some path is likely. And we remember the profile guided code positioning paper And I'd encourage you to read it, actually. That's a beautiful paper. I'll write it again. It's probably on the website, right, Justin? OK, Pettis and Hansen, Profile-Guided Code Positioning. That describes the basic idea of laying out code such that the likely path is a not taken path, and the benefits of this in terms of both instruction cache performance as well as branch prediction performance. And it's a general mechanism that's employed by many compilers today. The second, a little bit more sophisticated prediction mechanism, always to predict the branch as taken. The advantage, again, no direction prediction, no hardware direction prediction, right? And also it has better accuracy, right? Because most branches are taken. So loop branches are usually taken, right? Well, I cannot say that for sure, but many people write loops such that you iterate over those loops many, many times. Think about adding 2 arrays that are of size 1,000,000, right? How many times does that loop iterate? Lots, right? But of course, if the arrays are of size 1, how many times does that loop iterate? Only once, right? So loops can differ also. And we will see that will become a problem. So you get better accuracy, 60 to 70%, because backward branches are usually taken. Well, what is a backward branch? You know that the target address is lower than the branch PC, right? It goes backwards in program code. So people have actually realized something else as they looked at branch prediction. They figured out that backward branches are usually taken, but forward branches are usually not taken. So now people are starting to classify branches, right? In this case, when the hardware comes to a backward branch, it predicts the branch as taken. Otherwise, it predicts the branch as not taken. Does that make sense? Now, this is a heuristic, right? It's not always the case that forward branches are not taken. A forward branch can be taken, right? You may be jumping to some other places. What is a forward branch? And if else is a forward branch, for example. Where do I put these things? OK. It's over here? Where? Oh, thank you. OK. If some condition else, right? This is a forward branch. It could be, I guess, converted to a backward branch, but you'll need 2 branches for that. This is a forward branch. And again, it's a heuristic that this is taken or not taken, right? The good thing is forward branches can be made not taken easily by the compiler. It's harder to make backward branches not taken. So compiler, again, can take advantage of this prediction scheme. So this is a simple scheme that people have used that improves the accuracy over both of these. But now you need to do direction prediction, right? The hardware actually needs a predictor that figures out whether the branch is backward or forward. Or you know that whether a branch is backward or forward. How do you know that? You've decoded the branch, the previous instance of the branch. And you actually put that information in the BTB, right? So the BTB has a bit. In addition to the target address, it has a bit saying backward or forward, maybe, right? And the target address here. And this bit says if it's 1, it's backward. If it's 0, it's forward. And you fetch, you not only get a BTB hit, but also get the target address, but also get information about backward and forward. And now you can use this information to decide PC plus instruction size or the target address. Right? So that's how you implement it. But now you need more information in the BTB. OK? So these are simple static branch prediction mechanisms. Now let's get more sophisticated, because these, if you look at this, these two do not distinguish between different branches. These distinguish between classes of branches in a coarse way. But you can actually distinguish between individual branches so that we can become more accurate. Because maybe some forward branches are taken and some forward branches are not taken, right? So how do we distinguish between that? One idea is to use profiling. And we've covered that in the last 2 lectures, in the beginning of last 2 lectures, so you know that very well. Basically, a compiler or someone determines, in this case, let's say compiler determines likely direction for each branch using a profile run, using a representative input set, or maybe multiple profile runs. And based on that, encodes that likely direction as a hint bit in the branch instruction format. So we're going to extend the branch instruction format. It not only will specify opcode and the offset target for the computation of the target, but it'll also have a bit saying likely taken, let's say. And if this bit is set, the branch is predicted to be likely taken. If this bit is not set, the branch is predicted to be not taken. Make sense? And the compiler sets this bit. How does it set it bit? It determines the likely direction of the branch based on profile. Okay. Simple. So I guess what is the upside? I've already given you the upside. You get per branch prediction now based on the program counter of the branch. Based on the every branch, every static branch can have a different value for this bit. Right? So it's more accurate than the schemes in the previous slide. And you can imagine why, right? OK. Of course, it's accurate if the profile is representative. So we get back to the Achilles heel of profiling. If your profile is terrible, if you use the profiling input set that doesn't represent the real world, then this may not work very well. OK. So what are the downsides? I'll give you these quickly, and I'll ask you for it in the later slides, maybe in the next slide. What are the upsides and downsides? This requires hint bits in the branch instruction format now, where you did not need them previously, right? Why did you not need it for backward taken, forward not taken? Any guesses?
There's just logic to check the PC versus the target.
Exactly, yeah. You can have logic in the hardware that checks whether the target is before or after the program counter in the code. But now you really need this, so because the compiler needs to communicate information. Well, there's another downside, actually, because the accuracy of this actually depends on the dynamic branch behavior. So I'll use this notation throughout the lecture. This is the behavior of a single branch, and this is time. Imagine that as you go from left to right here, we're going through time. And the taken says this is the first instance of the branch was taken, next instance was taken, taken. I believe there are 10 of these. It doesn't matter. You have some number of takens and the same number of not takens after that. Regardless of how the compiler encodes this hint bit, you'll get 50% accuracy for this branch, right? Whether or not the compiler says likely taken or not likely not taken. And here also, right, another branch that flips between taken and not taken at every dynamic execution instance. So you could imagine branches display this behavior. And we'll see some cases from code that motivate you. So for example, you have this branch can flip between taken and not taken at every execution, right? Because your data set, maybe you have a data set. Maybe this branch is checking if input is even. And you can imagine how you can check that. And if your input, if you're taking your input from an array, and the array looks like this, 0, 1, 2, 3, 4, 5, connect the dots. Well, now you get a branch that's taken in one iteration and not taken in the next iteration, right? So it's easy to get these cases, especially when you have inputs like this. OK. So if you have a single hint bit, now you cannot adapt. So what's the problem here? The problem is you're making a single prediction for every instance of the branch. Right? You're not distinguishing between dynamic instances of the branch, which means that you're not adapting to the behavior of a branch itself. Now we're adapting to the behavior across branches because different branches have different hint bits. But within a branch, we're still making a single prediction across different instances. So the downside here is no adaptation to the behavior, dynamic behavior of an individual branch instruction. And that's the downside if you have a single prediction for a static branch, because dynamic instances are different from static instances. OK? And of course, we always have this problem, which I've already told you. Accuracy depends on the representatives of the input set. I guess in this case, it may not matter. You always get 50%, right? OK. OK, there's another way of doing static branch prediction, which is different from profile-based. Profile-based requires profiling, right? It requires some input set. So people have thought about, how can we do this without an input set, but still using compiler hints? And the idea is program-based prediction or program analysis-based. Program analysis, what does that mean? Basically, compiler analyzes the program, the data flow, control flow, and the semantic information in the program, and based on that, optimizes the code. That's the more general definition of program analysis. And we're going to see a specific instance of this. The compiler will look at the program somehow, do data flow analysis, figure out what the branches are actually doing, semantically, perhaps, right? And based on that information, estimate whether the branch is likely taken or likely not taken. Can you guess how this could happen? No profiling. We're not going to have any representative or non-representative input sets. Yes?
Like you said, loops generally are going to be happening a lot of times. So if you have like I less than length or whatever, chances are that one's going to be taken. But I don't know, maybe an if else, like a recursive if else, usually the if statement is not taken, like if n less than 2 return whatever. Usually that's not taken, so you could probably optimize that to be probably not taken.
That's right, exactly. Exactly. Once you detect a loop, maybe you're iterating over a loop that iterates over an array. In that case, you may decide that the compiler can detect a loop, right? In that case, the compiler can set the bit for that loop. Those are good examples. There are other examples too. Those are relatively simple examples the compiler can accomplish. It turns out you can actually do much more than this. So basically, well, I've given you the idea. Use heuristics based on program analysis to determine statically predict direction. For example, one heuristic actually that this paper, and I'd encourage you to read this paper also. It's called Branch Prediction for Free. Again, published in Programming Languages Design and Implementation Conference in 1993. That was published in 1990 in the same conference. Basically, for example, one heuristic is predict a branch, I think branch less than or equal to 0 based on this opcode. If a branch has that opcode, predict that as not taken. Why? Because it turns out negative integers are used as error values in many programs. It's not always the case. Again, this doesn't always apply, but it's a heuristic. And Ball and Lars determined that this is the case across many programs. Not based on profiling, but based on, one could say, intuition, or maybe past experience, right? But you can encode that into the compiler as a heuristic. So that's one example. That's beyond the compiler coding a loop branch as likely taken. So for example, another branch, a branch that's guarding a loop execution, it turns out these branches are usually taken. So you have a branch if some code loop, else do something else, or maybe there is no else. So this branch is guarding the execution of the loop. It turns out in most programs this branch is taken such that you execute the loop, because most programs actually execute the loops. Make sense? Or one example, actually this makes a lot of sense probably. If you're comparing pointers, 2 pointers, you guys are familiar with pointers, right? If p equals q to 2 pointers, maybe p equals some pointer to node, and q is equal to some pointer to node, usually it turns out that p is not equal to q, because 2 pointers are not the same. And again, this is encoded as likely not taken. Similarly, floating point comparisons are likely not equal. When you compare 2 floating point values, they're not equal likely. Make sense? There are a bunch of other heuristics. These are some of the interesting ones I thought that I would share with you. Make sense? OK. So what is the advantage of this? Well, it obviously doesn't require profiling now, right? The compiler simply analyzes the code and figures out if this is a branch that's doing a pointer comparison. And that doesn't require profiling. The downside is heuristics might not be representative or good, right? This is always the case with heuristics. Another downside is it requires compiler analysis and ISA support, but that's true for the other, any static branch prediction mechanism. But in this case, you're doing compiler analysis, not profiling. Well, the other downside is what I've described to you before. That's true for all static branch prediction schemes. So it turns out if you read this paper, you can get 80% prediction accuracy for branches if you apply a bunch of these heuristics together. Which you may think is pretty good, right? 80%. 80% of your branches are predicted correctly. OK, we'll get back to that 80%. But I think with pure compiler analysis, it's a pretty good branch prediction accuracy. The third is using the same infrastructure, which is the ISA support for a hint bit. Maybe the programmer can specify this hint bit, right? We've discussed this briefly last time. And the idea is programmer provides this statically predicted direction somehow. Of course, you need to have some infrastructure for this now. Right? Programmer cannot just say, well, assembly programmer can say this, but what about the high-level language programmer? How do you enable that programmer to say this? Well, basically, you add something called a pragma into the programming language that qualifies a branch as likely taken or likely not taken. Are you guys familiar with pragmas? Yes, some of you know some of you. OK. A pragma, let me skip, is essentially a keyword that enables a programmer to convey hints to the lower levels of the transformation hierarchy. It's simple. You have programming language, and let's say you have the compiler here, but you could have the runtime system also. Well, maybe underneath the compiler, I'll have the runtime system /OS, and then you have the ISA, right? Although you have multiple things depending on the dynamic static. But basically, somehow the programmer needs to convey that a branch is taken or not taken, and you do that using the idea of pragmas. The programming language provides this infrastructure to specify this. And an example in C is, for example, this. C has this pragma likely. If likely x says that this branch that checks x is likely taken. Right? And if you have this, the compiler actually says, oh, the programmer told me that this branch is likely taken. Now it's compiler's choice, right? Does it believe the programmer, or does it do some other thing, profiling, for example? Let's say we believe the programmer. The compiler sets the hint bit as 1, likely. And you could do unlikely also. For example, in this case, I've given you, it's unlikely that this error will be true, so this branch is unlikely to be taken. Right? So you could do this in your programs today. It's a very common pragma. OK, let's get back here. How many people use this, by the way? You do? Oh, you're optimizing your code. That's great. Do you see the difference? No. No, not at all? So these, well, I guess, do you know if the compiler is actually heeding your, it is. OK, so you actually analyze your code, and it's heeding. But you don't see the difference. Are you giving the correct or representative? So there's a lot of issues involved here, right? Which actually lead to advantages and disadvantages. So even if you may actually give it, maybe it doesn't matter, right? Maybe there are some other bottlenecks in your program. Good. OK, so advantages, now you don't require profiling or program analysis. Now the burden is somewhat on the programmer, right? And programmer may actually know better, right? If that is the case, this is great. Programmer may know some branches and their program behavior better than other analysis techniques. And you could potentially imagine this, right? If the programmer actually really knows the input that's coming into, or characteristics of the input, or most of the input, maybe they can actually say, oh, I expect a data set like this, maybe. Of course, I don't know what they will do with this data set, but maybe it's all zeros, right? Or maybe it's all ones. And actually, expert programmers may have that information if they actually know where their program is being used. Of course, this may not be true, and that's the downside also. So what is the downside one? It obviously requires programming language, compiler, and ISA, the entire toolchain support, right, across the hierarchy. And it perhaps burdens the programmer, right? Well, the good thing is you don't require the programmer to do this. That's why it's a pragma. It's a pragma, it's a hint. The programmer doesn't need to do it. But if this is the only thing you rely on for your static branch prediction, it does burden the programmer probably. Okay? So pragmas are actually a very powerful way of conveying information from the language to the compiler and downstream. Many other hints and optimizations can be enabled with them. For example, whether a loop can be parallelized. How many of you have done parallel programming? Many? Some of you are doing it, I know, in some other classes. Are you enjoying it? Okay. Yeah, it's a tough task, right? And it's hard for the programmer to do it. It's hard for the hardware to do it also. And who does it? Maybe we'll have a lecture that describes what are the trade-offs. Again, you can do it in hardware. You can do it in the programmer. You can do it at the programming language level. You rely on the programmer. But programmer can specify whether a loop can be parallelized. This is a very common. OpenMP is a common parallel programming platform. And those of you who are doing parallel programming may have used this pragma. In front of a loop, you add this pragma, OpenMP parallel. And that means that the programmer says this loop can be parallelized to the compiler. Now again, it's the compiler's choice to believe this or not believe this, or use this hint or not use this hint, right? That's why it's a pragma. It's not a directive. It's not saying if X, do this, right? It's basically a hint. The compiler can generate sequential code for that loop, or the compiler can actually try to parallelize that loop by distributing the input set, for example. If it's an input, if the input is an array, the compiler can try to parallelize that array by having multiple loops that operate on different portions of the array, right? By using that hint. And this is a definition from the web that describes the OMP parallel directive explicitly instructs the compiler to parallelize the chosen segment of the code. Okay? So this is an aside in pragmas. There are many other pragmas that you can think of. For example, the programmer can specify whether a load can hit or miss, right? Most of the time, I think that this load will miss in the cache. And again, that could aid instruction scheduling somehow. Okay. So you realize this probably, but we've discussed 3 techniques for static branch prediction, and all of the 3 can be combined, right? You could actually do all, profile-based, program-based, or programmer-based, because they all use the same infrastructure, which is this instruction with a hint bit. The question is, how would you do that, right? When would you? Of course, if you do not have programmer information, now you're up to profile-based and program-based. But how do you combine these two? I don't expect you to answer this, but there are a lot of trade-offs associated with it. Yes. One last question. What are the common disadvantages of all 3 techniques other than providing ISA support? I think it's on the board, actually. Right. None of these techniques can enable adaptation to the dynamic behavior of an individual branch. Because of this, you have a single bit per static branch. You don't distinguish between dynamic instances. Basically, it cannot adapt to dynamic changes in per branch behavior. But you can actually mitigate this a little bit, right? If you have some other infrastructure, which is this thing over here that I put, which is the runtime system, right? Or you could think of this as a dynamic compiler, right? Or maybe virtual machine. They're relatively similar, actually. What you can do is periodically recompile the code while it's running. That's the idea of a dynamic compiler. Periodically, you instrument the program. You figure out what are the hot portions while the program is running. And after a while, if the hot portions of a program change, you invoke the compiler that says, I'm executing this program, and recompile it while I'm executing it. That's the idea. And if you can do that, now you can adapt. You can set this bit to something else, right? And if you have this information about, well, hopefully you have that information about what are the hot paths of the code, right? But this requires a lot of profiling information that needs to be collected while you're running the program, right? The program needs to be instrumented with that. So there's some overhead. And you cannot do this at a very fine granularity because of that overhead, right? You cannot say, I'm going to change this bit at every instance of execution. That's going to be tough probably, especially if that branch is very frequently executed. And there are branches that actually change their direction at every instance of execution, right? An example is this one, the branch that's checking if the input value is even or odd. So you could mitigate some of these concerns with a dynamic compiler, but you cannot actually do this at a very fine grain, do perfect branch prediction at a very fine grain. So our goal is to try to make this perfect, get that branch right maybe. Okay? Okay, that's the idea of dynamic branch prediction. Basically, predict branches based on dynamic information that the hardware collects at runtime. Let's cover the advantages. Now you can actually do the prediction based on the history of the execution of branches. You can collect the history of an individual branch or across different branches, and we will see the benefits of both in this lecture. And based on that history, you can say, oh, based on the last 3 times this branch was executed, I saw this. So the next time I'm predicting that I'm going to see this. That's one example. And which is more powerful than this, right? Because here there is no history. You could argue that the history was actually static, or history is based on program analysis. But that's not history. That's not dynamic history. Which means that now you can adapt to the dynamic changes based on branch behavior. Well, obviously, you don't need static profiling anymore. Input set representativeness problem goes away. Right? That's always the case when you put something into hardware and it adapts to dynamic behavior. So this is a general advantage. Now, this advantage is more complex. As we will see, this requires additional hardware. Because now you really need that direction predictor sitting with some table detecting the history of a branch. OK. So one simple dynamic history-based branch predictor is last time predictor, right? That's the simplest you can think of. The idea is you have basically, well, I guess the idea is not given here, but you can guess the idea. Predict the direction of the branch as the direction the branch took in its last execution. And forget this because it's not going to work here, right? It's going to work for something else. That's the idea. What does this require? Basically, single bit per branch. In the BTB, you have another bit saying, what happened to the branch last time? Direction of the branch last time it was executed. And when the branch was executed last time, it updates this bit. Taken, let's say. And when you get a BTB hit, you not only get the target address, but you also get the last time prediction. Well, that's taken or not taken prediction. You have a single bit prediction, right? That's the idea. And it's easy to do, right? So if you look at this, remember this taken branch that flips to not taken for the rest half of its execution. And remember that we got only 50% branch prediction accuracy with static branch prediction. Now I can get 90% accuracy here, right? Correct? How do I get 90%? Let's say initially we mispredicted it. But once it's taken, the next time it's executed, this time it's executed, the branch will be predicted taken, and you'll get it correct. Next time, you look at last time, it was taken, so it's going to be predicted taken, which is correct. Dot, 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 dot. Now you get misprediction when you flip the direction, right? Here, when you execute this branch here, when you fetch this branch here, the previous time it was executed was taken, but it will be predicted taken here, although it's really going to be resolved as not taken. So you mispredict in the first case, and you mispredict whenever the branch flips directions. So in this case, I think you mispredict twice out of 20 times the branch is executed, which means you get 90% accuracy for this branch. That's a lot, right? 90% for a branch like this. I guess one downside of this is it always mispredicts the last iteration and the first iteration of a loop branch. If you think of this as a loop branch, or maybe this is not the best example, but you have a loop. Oh, we did not cover this, right? erase it because probably I'll use it. So you have a for loop. I guess I less than n, I plus plus. Oh, I guess I should do that first. Basically, if you look at the execution history of this loop, it will be taken, taken, dot, 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 taken when you enter the loop the first time. And when you exit the loop, it'll be not taken. And let's say you have another loop here. This is a nested loop or something, for or while. Later, you get back to this loop again. And when you enter it, the first time you execute this loop, it'll be predicted not taken. But actually, it's taken. The execution will be taken. So it'll be taken while the loop iterates internally. And when you exit that loop, it'll be not taken again, right? So if you look at this loop branch, every time you exit that loop, you get a misprediction, right? So you exit the loop here. The next time you enter the loop, well, you exit the loop here. It becomes not taken. But you predicted taken, so this is mispredicted. And the next time you enter the loop, the last time the branch was executed, it was not taken because you exited the loop. But you predicted not taken. But you should have predicted taken because you entered the loop and you're actually going to iterate, right? This is assuming a loop that actually iterates a lot. So you mispredict this branch twice. When you exit the loop and when you re-enter the loop. Same here. So if this loop is executed, if this loop is overall its execution and executed n times, you get n minus 2 correct predictions. So your accuracy is n minus 2 over n. Now, if your n is huge, this is great, right? If your n is a billion, you only get 2 of the, meaning if this loop is executed a billion times iterations over the execution of the entire program, you get great accuracy. But if your n is 10, well, that may not be good, right? Okay. So if your loop is short, meaning whenever you execute this n is a billion, this is great. But if this n is 3, that's not good, right? Now you're mispredicting this loop twice. 2 out of 3 times. OK? And you can imagine cases where this n is 3, right? Maybe, yes?
I have a question. Why is there an x under the t on the far right?
Oh, here?
Yeah.
So this is the case where you're iterating over the loop and you're exiting, falling through. This is the last exit. Oh, OK. You're right. So it should have been here, right? Absolutely. So this is correctly predicted because the previous time the loop branch was taken, but the next time you're exiting the loop, so you predicted taken, but it should have been predicted not taken. Thanks. Okay. So this depends on how many times your loop actually iterates, right? And there are actually loops that do not iterate a lot. Okay. I'll give you one example. So if you actually have let's say you're searching for a key in a hash table. What do you do when you search for a key? Basically, you index into a bucket with some hash. And this bucket actually contains the other keys that you're going to search for. Key 1, key 2, key 3. If this linked list is relatively short, this loop may not iterate a lot, right? If your hash table is nicely balanced. So you may have a while loop where the iterations are few. Not all of programs operate on huge arrays. Okay? So in that case, this may be bad. Okay, so this is great for loop branches for loops with large number of iterations. But loop branches for loops with small number of iterations, and this is the worst case for that, it's not good. This is a loop branch where n is 1, right? n can be 1 because, well, if you look at this, this could be a very short linked list, right? That's one example. So in this case, this is the execution history of the loop branch, taken, not taken, taken, not taken, taken, not taken, taken, not taken. You get 0% accuracy. Terrible. We're trying to adapt to dynamic branch behavior per branch, but we're doing worse than static branch prediction, right? If you look at the static branch prediction, regardless of the way you encode this, you get 50% accuracy. Okay, so how do you fix this problem? Well, you don't do last time, maybe. That's one fix, right? So how do you not do last time? So what is the problem here? Well, we're going to have a hack meeting to fix this problem, and we're going to hopefully fix this in a better way. Yes?
You could store another bit of information in the BTB is like how accurately have I predicted this the last couple of times, something like that. And then if you get 4 or 5 in a row that you didn't, then you could just stop doing it that way or something.
Okay, that's good. I like that idea. We'll get back to that. That's the idea you suggested. It says, how accurate was my prediction so far, or in the last few times for this branch? And based on that, you change strategies, right? Maybe you switch to static branch prediction in that case, right? If you figure out that you're not doing so well in your dynamic branch prediction mechanism. That's called actually branch confidence estimation. You basically estimate how confident a prediction mechanism is in its prediction. And you could do it the way you suggested. And maybe you can change strategies. That's not the solution I'm going to describe, but keep that in mind. That's potentially a good solution. And we're going to use that for something else later on. Yes?
You could have a bit that says you should take the branch that wasn't taken before.
You should take the branch that wasn't taken before.
Yeah.
Say it again. What does that mean exactly in this case?
So it would accurately predict Tn, Tn, Tn.
I see. That's specializing for this case though, right? We want to be general. But you're right, you could actually specialize for different cases. And we're going to try to do something like that later on. You can detect this pattern, right? You can actually have a branch prediction predictor that works on pattern detection, and we're going to look at that, something like that soon. Yes?
Predictor with more history?
More history, yes. Well, I'm going to ignore this for now, but that's the idea, yeah. We're going to look at more history. But I guess let me go through this. Basically, the idea is maybe you're changing your decision so fast, right? Maybe, well, there are many ways of doing more history, but one way of doing more history is maybe you should stick to taken prediction in this case, right? Or not taken prediction. So don't change your decision too fast. If you don't change your decision too fast, you get 50% accuracy here. For example, if you don't do last time, but you look at last 2 times, and last time says it was taken, the next time it was not taken, but you don't switch to taken quickly. So you still predict taken, and you keep predicting taken until you see not taken twice. Right. That's the idea, adding a little bit more history, or hysteresis to the branch predictor. This is also called hysteresis, but we will see that. So let's take a look at what's the infrastructure for this, because I'm going to build that history on top of this. So if you look at this, last time predictor actually can get a lot more cycles, a lot less cycles per instruction if you assume 85% accuracy. And I've already given you that you can do it with 1 bit per branch in the branch target buffer. Or you could have a separate direction predictor that stores this 1 bit per branch. And you could study that slide. Basically, you need a finite state machine that predicts taken. If the branch is actually taken, you stay in that state. If the branch is actually not taken, you go back to the predict not taken state. And this is how the 0 and 1 bits are updated. So how do we improve upon it? Basically, maybe we're being too quick in our decision, right, in our prediction. We're changing from taken to not taken and not taken to taken too quickly. Even though the branch may be mostly taken and mostly not taken. Right? So this is especially apparent if you have something like this, right, a loop iteration like this. You're mispredicting the loop twice because you're looking at the last time. But if you actually think about the last n times, the loop is actually mostly, the loop branch is actually mostly taken. Right? So don't switch your decision in one contradictory outcome. That's the idea. Basically, we want to add hysteresis to the predictor such that the prediction does not change on a single different outcome, or n different outcomes from the past outcome. Well, how do you do this? Basically, it's 2 bits to track the history of predictions for a branch instead of a single bit. Make sense? Now we can have 2 states. Remember that state diagram? Instead of 1 state for taken, 1 state for not taken, you can have 2 states for each. And I'll show you that example. So this is a very good paper, actually. I didn't assign you this, but if you're interested in the origins of some of these predictors, this is Jim Smith's paper in ISCA 1981 that describes different branch prediction strategies at the time. This is very old. This is 32 years old now. We're all getting old, huh? But we're going to see much more sophisticated predictors. But this is a nice paper that describes the state of the art at the time and introduces this predictor. So what is the idea? Instead of having a single counter for each branch, have a 2-bit counter. Now we're going to add 1 more bit here. And now if you have a strong prediction, you encode the taken state as, for example, 0, 0, 0, 1. And if you see a not taken outcome, you go from the strongly taken state to a weakly taken state. This is the prediction state. And when you fetch the branch next, you still predict the branch taken, even though you've seen a single outcome that says when the branch was executed, it was not taken. Right? If the next time you see the branch executed as not taken, now you go to the not taken state. That says, oh, I've seen not taken twice, so let me now start predicting it as not taken. Right? And if you see not taken again, you go to another not taken state, which is strongly not taken. I've seen at least 2 not taken states, so I'm going to predict it not taken again. That's the idea. Simple. More history. So what is the benefit? We're going to see the implementation of it, the state machine, but I'm basically giving you the idea. The benefit is, now if you have a loop with n iterations, your misprediction happens only once. Right? I guess I've eliminated my own loop somehow. I'm going to bring it back. This was the history of the branch, right? And we were predicting every time, twice. Once when we exit the branch, once we exit the loop, and once again once we re-enter the loop. Now what's going to happen with this 2-bit counter branch prediction is, when we execute the branch that is supposed to exit the loop, we're going to predict it as taken. Right? So we're going to get it right. Oh, no, we're going to get it wrong. Sorry. We're going to predict it as taken, but it's going to be not taken, so we're going to get it wrong. When we re-enter the loop, we're not going to make the mistake of predicting the branch as not taken, because we didn't change our decision, prediction decision, based on this single not taken outcome. We're going to get this right. And we're going to miss this exit branch again, because we're going to predict the loop as the loop exit branch as taken, but it's actually not taken. We're going to get it wrong. But when we re-enter, we're going to predict it as taken, because again, we didn't change our decision or prediction decision based on a single different outcome. So now you get an incorrect prediction only once out of n iterations, n minus 1 over n, which is now much better than n minus 2 over n for values of n that are small. In fact, I guess you could argue that it's infinitely better for this, or undefinedly better, because you get 50% accuracy instead of 0% accuracy. Make sense? Of course, there is some assumption here, because the assumption is that you'd better start with taken here for this particular case, right? Weakly taken. Does that make sense? OK. So what you get is better prediction accuracy. And if you do something like this, let's say you get 90% accuracy, you're getting closer to 1 cycles per instruction. But now you have more hardware cost. What is the hardware cost? Again, 2-bit counter. So it's not that bad. The hardware cost is not that bad. So if you actually look at the state machine of this, so what did we actually employ? We actually used saturating arithmetic here, right? There's a symbol for maximum value and a minimum value. You guys know about saturating arithmetic? Good. So you could actually, you don't need to do this with 2-bit counters only, right? You could actually do this for with 3-bit counters, right? But let's do it for 2-bit counters. We have 4 different values, 0, 0, 0, 1, 1, 0, 1, 1. And your counter has a minimum value and a maximum value. And once you increment the counter beyond your maximum value, you stay at 1, 1. So your counter saturates, right? You don't overflow. You don't go to 0, 0 if you do that. Now that will be bad for our prediction mechanism. And you have a minimum value, which is 0, 0. And if you decrement this counter, it stays at 0, 0. It saturates at the minimum value also. That's the saturating arithmetic. OK. So that's our counter. That's our 1, 1 state. And that's the predicted taken state. We're going to call this strongly taken. So we strongly believe that this branch is actually going to be taken. And if the branch is actually taken, based on the outcome, we're going to still strongly believe that's going to be taken. If the branch is actually not taken, well, now our confidence or our belief was not satisfied in this case. So we're going to go to a state where we're going to weakly believe that it's taken, right? And we're still going to predict it taken because we still believe that it's taken. It's going to be taken. And when we see if the next outcome is taken, we predicted it correctly, we're going to go back to the state where we strongly believe that it's taken. Right? So now you can follow this. If you're believing that it's weakly taken, you're weakly believing that it's taken. But you see not taken, now your belief has changed. Right? Now the counter goes back to 0, 1. So it should be weakly not taken. Now you're starting to believe that it's actually not taken. I'm doing the wrong thing. Now, but your belief is weak. So if you see a taken outcome here, maybe we're going to change our belief, right? In that case, the counter moves from weakly not taken state to weakly taken state. And you can continue this. If you keep seeing not taken, you're going to strongly believe that it's not taken. If you keep seeing taken outcome for the branch, you're going to move to a state where you more strongly believe that it's taken. That's the idea of hysteresis. Now you can expand this, right? You can expand this to 3-bit counters. Right? You can expand this to 4-bit counters. How many incorrect outcomes, incorrect predictions do you need to see to change your belief or prediction? That's the idea. It doesn't need to be a counter also, right? We can imagine different state machines. We're not going to cover all of them, but this is one of the most commonly used state machines, 2-bit counters, because it adds some hysteresis. And you could, for example, the place where you draw the distinction can be different, right? Maybe this state space is actually not taken, and all of these 3 states are taken. You could imagine different designs. This is where things become a little bit hocus pocus, maybe, right? Black magic. How do you actually design the state machine? What is the right thing? If you really understand how most of your branches behave, maybe you can actually design a better machine. But this is one of the most commonly used state machines today. OK? Any questions? OK. I think I've given you this. Basically, you can follow these. You change prediction after 2 consecutive mistakes in this case with a 2-bit counter. With a 3-bit counter, actually, you need how many consecutive mistakes? Is it 4? 4, right? Yes. Assuming you divide your state space equally between not taken and taken, right? You could actually have a finite state machine that changes its belief very, very quickly, right? Goes back to from strongly taken, strongly not taken. I don't know why you would do that, but maybe you have some other conditions that's input to this. OK. So is this enough? We're making this thing more complicated now. not that bad, and it turns out actually you get 85 to 90% prediction accuracy with this kind of state machine in most programs with this kind of prediction. It's also called bimodal prediction, by the way. If you hear that, what is bimodal prediction? This is bimodal prediction. I don't think there's a good reason for that name. Could have been better. But 2-bit counter prediction is another name. Is this enough? I guess this depends, right? How big is this branch problem? This depends on, again, your design point as well as what you view. Like what does this buy you in terms of performance? For this pipeline, I'll go back to this. Maybe 1.04 CPI is not too bad, right? 90% accuracy. With a 2-bit, if your 2-bit counter branch prediction provides you 90% accuracy, if you do the calculations that we've done in the previous lectures, you get 1.04 cycles per instruction. Not bad for this pipeline, but remember our branch misprediction penalty for this pipeline is only 2. So we can resolve the branch after 2 cycles. We get 2-cycle bubble if we're wrong. So let's take a look at how big is the branch problem. Let's rethink it. We're going to assume that control flow instructions are reasonably frequent, 15 to 25% of all instructions, which is actually demonstrated in many works before. The problem is, again, next fetch address after control flow instruction is not determined after n cycles in a pipeline processor. Now, if n is 2, maybe this is enough. And what is n cycles? N cycles is actually the minimum branch resolution latency. So we resolve branch after n cycles. I'm going to call it minimum because with out-of-order execution, actually, this n cycles can be variable, right? Because you're fetching a branch, and when you execute that branch is dependent on the latency of all of the previous instructions. And stalling on a branch wastes instruction processing bandwidth. It reduces IPC. So what is that wasted processing bandwidth or increases CPI? Let's think. I'm going to now assume a superscalar processor because the problem becomes even worse with a superscalar processor. It's still bad as n increases. So we're going to look at n. This is our pipeline depth. So you have, let's say, fetch, decode, ... And after n cycles, you actually resolve branch. I'm going to add a stage. It could be an execute stage. You resolve the branch, and now you can fetch the next instruction. And this is going to be our n. I'm going to also add another variable, which is issue width, or maybe I should call it fetch width also. That's called issue width. This will become more clear. But the idea is how many instructions actually you're fetching concurrently. So this is the first. Maybe you're concurrently fetching another instruction. And you're fetching another instruction in parallel and executing them in parallel. Remember, this is superscalar execution. You're fetching, decoding, executing, resolving multiple instructions per cycle. And what is that? This is the IW instructions fetched per cycle. Let's say only one of them is a branch. Now, if you mispredict a branch, you're not only wasting n of the previous instructions, but you're also wasting everything that comes after that branch, which is n times IW instructions, right? For example, if you have a pipeline that's 20 stages deep, and if you have a pipeline, if you have a machine that's 1, 2, 3, 4, 5 instructions wide, you're actually wasting 100 instruction slots if you mispredict a branch, right? Because you fetched 100 instructions after that branch before you resolve it. Does that make sense? So it's a lot of instructions. So, well, So we're going to assume the things that I've told you. 5-wide superscalar pipeline. So you're basically fetching 5 instructions per cycle. And 20 cycle, and n is 20. 20 deep pipeline. Now let's take a look at how long does it take to fetch 500 instructions. Maybe I'll ask you to do some of these calculations. We're going to do some assumptions, of course. Make some assumptions, of course. Assume no fetch breaks. Let's first of all assume 1 out of 5 instructions a branch, conveniently. And that occurs every cycle. Every cycle you fetch 5 instructions and you know that one is a branch. Nice, beautiful, right? And we're going to assume the first instruction is a branch. First instruction out of those 5 is a branch. We're going to assume no fetch breaks, meaning that branch doesn't branch into that particular block. Or we're always fetching 5 instructions. What is a fetch break? Fetch break, I'll define it, I guess. You've actually read this in your first paper that you read, the Yale PAT paper that describes processor evolution, right? It talks about fetch breaks. Fetch break means you have some issue of instructions. You can actually fetch 5 instructions, but for some reason, you cannot fetch 5. You fetch only 1. Why? Because in the middle of the fetch, you get a cache miss. Right? We're going to assume that that's not the case. Why? Because your branch is actually jumping somewhere out, so you need to access the iCache again. Right? So we're going to assume that's not the case. Again. We're going to assume that we can always fetch 5 instructions, and the first instruction is a branch. Let's assume 100% accuracy, branch prediction accuracy. Every branch is predicted correctly. And we're fetching 1 instruction, 1 branch per cycle. So how many cycles does it take to fetch these 500 instructions? That's the first simple part of the question. We want to fetch 500 instructions, 100% accuracy for branches, and we're fetching 5 instructions per cycle. How many cycles? 100, right? 100 cycles. Because 500 instructions, no mispredictions at all, and we're fetching 5 beautiful, correct instructions per cycle. 500 divided by 5 is 100. So all instructions fetched are on the correct path. We're not flushing anything. No wasted work. So we like this, right? 100% accuracy. Well, let's go down to 99% accuracy. How bad does it become? How long does it take to fetch these 500 instructions now? With these assumptions. It's not that hard, actually. It's not that bad, right? 120, yes. Maybe you've done some 1 order of magnitude calculation mistake, which is easy to do, actually, with this question, with the way the question is stated. But yes, it's 120. You can think of it as you've got to be able to fetch 500 instructions, right? And that will take 100 cycles regardless of whether or not you have a branch misprediction. But you, out of these 500 instructions, you're going to have a misprediction every 100 branches, right? Which means that 20 of the let me see. You're going to fetch 20 times 5 incorrect instructions, right? Because how many branches do you have in this? Well, you have 500 branches, right? Oh, no, you have 100 branches, right? And you're going to predict 1 of them incorrectly. So it's going to take 120 cycles for you to fetch all of these instructions. Does that make sense? Everybody's clear on this? OK. So now that you understand this, which means that you get 20% extra instructions fetched, right? You're fetching 20% additional instructions. Now make it 98%. Well, now you're doubling the amount of cycles you spend on the wrong path, right? Basically, you need to have 100 cycles to fetch the correct instructions, but you're wasting 20 times 2 cycles on the wrong path, 40 cycles. You have 40% extra instructions fetched. Instead of fetching 100 cycles, you're fetching 140 cycles. And remember, we're always fetching 5 instructions per cycle. 95% accuracy. Now you get to 200 cycles. Right? Basically, 100 cycles to fetch correct path instructions. And you actually mispredict 5 of these branches. Right? Instead of mispredicting 1 of those branches, we've actually mispredicted 5 of those branches. Which means that 5 of those branches are mispredicted. 5 times you're paying the branch misprediction penalty of 20 cycles. Only after 20 cycles you can recover. So now you take 200 cycles. And 100% extra instructions are fetched. So you wasted half of your bandwidth in the machine. With even a 95% accuracy, and we're not even at 90% yet. If you do this calculation for 90%, you'll get 300 cycles, right? And you're fetching 66% of your instructions that you're going to discard. 60% of instructions that are fetched are going to be discarded. So this problem becomes big if you actually design a large machine. So people have spent a lot of effort to optimize it. But the question is, can we do better? And I think, let me give you the basic ideas, and we'll take a short break, and then we're going to continue. Basically, doing better means doing something better than last time predictability. We're actually looking at last time predictability, even if you have a too big counter prediction. What happened to this thing last time? But people have realized 2 things. One is the outcome of a branch actually can be correlated with the other branch's outcomes. So if you look at the outcome of a branch that's here, maybe it'll indicate something about this branch. This is called global branch correlation, and we're going to take advantage of that. And people have also realized that a branch's outcome can be correlated with past outcomes of the branch, other than the outcome of the branch last time it was executed. So the branch can follow some patterns. This is called local branch correlation, and we're going to take advantage of this also. So before starting global branch correlation, I guess let's take a break for 3 minutes. Look at global branch correlation first. How do you use a branch's outcome can be correlated with other branches' outcomes? So why is that the case, basically? Well, recently executed branch outcomes in the execution path is actually correlated with the outcome of the next branch. And I'll give you some examples. You can imagine how these occur in real programs. For example, you have these 2 branches. The first is testing condition 1. The second is testing condition 1 and condition 2. And you do something if the branch is taken. Now, if you look at the second branch, if the first branch is not taken, you know that the second branch is also not taken. Right? So can you leverage this information about the recently executed branch? That's the idea. Another example. This branch here, based on some conditions, sets some data value. A later branch tests that data value. And these are actually examples from real programs, abstracted away, just to show you the correlation. In this case, if the first branch is taken, which means that A is set to 2, you know that this branch is not going to be taken. Nice. So can we actually use that information? Another example. This branch does something if condition 1 is true. This branch does something if the condition 2 is true. And this branch does something if both condition 1 and condition 2 are true. Now, if y and z are both taken, then x is also taken, right? Whereas if y or z is not taken, then x is also not taken. So can we somehow exploit this correlation that happens across these branches that are different? They're at different program counters. Well, one real example actually that looks at something like this. This is from a program that was in the benchmark suite in 1992, SPEC benchmark suite. You guys know about SPEC? It's called the Standard Performance Evaluation Corporation. It actually is a consortium of companies that get together and develop benchmarks or accept benchmarks to measure performance of microprocessors and platforms. And they have a bunch of different benchmark suites. This used to be the common benchmark suite, SPEC CPU benchmark suite, that tests the performance of a CPU at the time, basically a processor for CPU bound applications. And they had this application, Untitled, which actually, I think it does display truth tables based on Boolean equations. And this was actually a hard case for people to optimize the benchmark, optimize the performance for. And this was one of the reasons. You had this branch, AA is tested to be for 2, and you set AA to 0 if that's the case. BB is tested for 2, and BB is set to 0 if that's the case. And then there's another branch that tests if AA is equal to BB. Right? So now if you look at this, if B1 is not taken, right, and B2 is not taken, then B3 is certainly taken, right? You know that information. So that's global. It turns out that if you actually have a global branch predictor, which I will describe, you get this branch accurately most of the time based on the input set. So a global branch predictor made a big difference for this particular benchmark. And it was an important benchmark for its time. They've eliminated this benchmark later on from the suite. I guess there is we could have a lecture on benchmarking also. But this will give you an idea on real applications have this behavior, this kind of correlation. Okay, so how do you capture something like this? The idea is associate branch outcomes with the global taken or not taken history of all branches. So instead of having a history for a single branch, why don't we have a history of all branches? Let's say all recent branches that we've executed. No. Well, what is that? That's basically a global history register. You have this, what I'll call a global history register. And you can write down the long form, which basically tells you the direction of last n executed branches. What does this mean? This history register is n-bit wide, right? Okay? And let's say this is the last executed branch. It could be taken, right? And then the previously executed branch, it could be at a different program counter, it could be not taken. ... and you have nth previously executed branch could be taken. So you form a history, and you encode this with zeros and ones. And that history is used to index a table of counters, maybe, that says, the last time I saw this history, the outcome of the branch that I'm fetching was taken. So this time I'm seeing this history again. I'm going to predict the branch as taken. That's the basic idea. Right? Beautiful and simple. Now you can think about different ways of forming the history. But that's the basic idea. Make a prediction based on the outcome of the branch the last time the same global branch history was encountered. How do you implement it? This is what I've shown you, the global history register. And you use that history register to index into a table that recorded the outcome that was seen for the global history register value in the recent past. So now I've given you one bit here, but this could be, again, this is called a pattern history table. Pattern history table. Basically, you can think of this as a pattern, right? You have a pattern of branch outcomes, last n branch outcomes. You use that pattern to index into this table, and that gives you the history of that particular branch that had the same pattern of execution the previous time. But this doesn't need to be a single bit. This can be a 2-bit counter, right? Let's make it a 2-bit counter. This can tell you, basically, the last n times I've seen this history, what happened. Okay? So you don't change your decision. What might happen here is the next time you see the history, you can flip direction, right? You can actually execute the branch. You may have the same problem that we've seen. You can change your prediction too quickly based on a single different outcome, right? Whereas if you have 2-bit counters here, you don't change your prediction too quickly based on a single different outcome seen for the same history. That's the idea. It's also called a global history predictor or global branch predictor. Now, what we're really doing is we're using 2 levels of history. It's also called 2-level branch prediction. You're keeping track of history of past n branches. This is the first level. And you're keeping track of history of the branches that were executed at that particular pattern, when you saw that particular pattern, because this also records some history, right? 2-bit counters looks at what happened to that particular branch or particular set of branches that happened to have that particular pattern. So this is the second level of history. Okay? And this is, I guess I've already given you what I've already told you. So what happens when you execute this branch? Basically, you shift this history out. You shift out the oldest branch, and you shift in the outcome of the branch that you execute. And you can read this paper that introduced this 2-level branch prediction, Micro 1991. Okay. So why does this work? I've already given you examples, but this is a nice example over here that shows why it works, because it has a good mapping of the global history to the direction of the branch. So if you look at this simple example, a for loop that iterates 100 times and another for loop that iterates 3 times, let's take a look at the conditional branches that test here. And let's say this is the steady state. We've actually warmed up all of these predictors, because you'd like to be able to see this history at least once to be able to do that prediction, right? Just like what we've seen before. So at that steady state, let's say we're testing this J value. What is the value of the global history register in that case? Well, if you look at the past 4 branches, let's assume that the global history register contains 4 branches or 4 bits. Your history should be, this is the latest branch, taken. Well, I guess I'll have to figure out what is the value here. J equals 1. Okay, your history should be 1101, right? What does that mean? Basically, you've executed this loop once. You've seen that as taken. And the last 3 iterations was not taken, right? Is that correct? Actually, let's start with something else here. Let's test this value, I less than 100. When you're testing this value, you're trying to predict that branch. Your history is like this. The last 3 times you've executed this branch, they were all taken, right? And the previous time this loop was not taken. So when you see this history, you're going to predict, you better predict that this branch is usually taken. Right? Does that make sense? And if you look at this, if your test is this one, you've shifted that branch once to the left. You've shifted the new outcome. The branch is actually taken. This loop was taken. And your history is 1101. So your result will be taken because you're in this loop. And if you actually execute this branch again, you shift the global history to the left by 1. Your global history is 1011. And you're still in this initial loop, so your result should be taken. Now, if you see this history 0111, this means that the last 3 branches were actually taken. So you're in this loop, and this previous branch was not taken. And you're going to get out of the loop. That means that the result should be not taken. So you can associate these histories with the results. You can study this a little bit more in the reading that I've assigned to you in the optional reading. But basically, your history, the previous histories of these 2 branches together, give you a good prediction of both of these branches. Okay? Any questions on this? This is just one example, but if you can imagine how this could potentially work for these more complicated cases also. Okay. So this is actually not something theoretical. This kind of predictors have been implemented in processors all along, starting with the Pentium Pro. Pentium Pro had this 4-bit global history register, and it had not a single pattern history table, but actually multiple pattern history tables. So you would have this 4-bit register, and that would index into 4 different tables. I believe it was 4 different tables. And you would get 4 different 2-bit counters as your prediction, and you would select one of those based on the program counter. Basically, you're kind of partitioning your space of these tables between different program counter sets. So that's how that predictor worked. But the same idea, the basic concept is you use this global history to predict the direction of the branch. Okay? And you can read more about that. Although I haven't assigned any Pentium Pro readings, but you can search for that and figure that out. Pentium Pro is relatively old now. So how do we actually improve this global predictor's accuracy? Well, what people have found is maybe this history is not enough, right? Maybe we're missing some information here. Because now we're just looking at this history. We're not differentiating between the different branches that have the same history. Well, Pentium Pro actually did that a little bit. It actually partitioned based on it took into account program counter information also in this history. Based on some bits of the program counter, you actually pick from different table. But you can do it another way. You can add more context information, which is what this is, but you can add that context information in a different way. And one is called the G-share predictor. This is global history register. Instead of indexing to this pattern history table with just the global history register, what you do is you XOR that global history register with the program counter of the branch or the instruction that you're currently fetching. Now, what has this done? You don't only take the history, but also take the program counter information into account. Once you've seen this history at this program counter, the last time that branch was taken or not taken. Nice, right? And that's the example from the paper that I've assigned. So it gives you more context information, and you can actually imagine other things here, right? Maybe you look at what was the call return stack behavior. What was the last call you've executed at that point in time? People have looked at things like that. This also gives you one more benefit, which is now you're better utilizing your pattern history table, right? This gives the hashing effect. So it reduces the conflicts in this pattern history table. The same history maps to many different places based on the program counter. And we'll get back to that when we talk about caching. The downside, of course, now it increases your access latency, right? You've added this XOR. Is this interesting? More black magic, right? But there's a reason for this black magic. This may actually look like black magic, but all of these add information to your prediction. Global branches, global history works because branches are correlated, and maybe you do actually want to take into account the branch address also, because branches, for example, there may be some branches where the last 4 global branches are taken. 1, 1, 1, 1. Your history is 1, 1, 1, 1. But different branches may behave differently based on that 1, 1, 1, 1, right? That's what this does. It gives you differentiate between different program counters. Okay, so let's recap a little bit because we're going to get more complicated. Remember, this was our one-level branch predictor. We took the program counter, we indexed the BTB, we also indexed this direction predictor of 2-bit counters, which could be incorporated into the BTB itself, actually. And that's what we got. 2-level global history predictor, we not only use the program counter to index, now we use the program counter just to index the BTB, and we use the global branch history to index the direction predictor. Okay? And G-share predictor, 2-level G-share predictor, we use a program counter to index the BTB, and we use a global branch history XORed with the program counter to index the direction predictor. Okay. Can we do better now? Well, before doing better, we're going to do it differently. This was global branch correlation. The second realization is that a branch's outcome is actually correlated with itself, other than the outcome of the branch last time it was executed. Local branch correlation. Let's take a look at that. This is another example from the paper that I was assigned. If you look at this, it's a single branch, right? And if you read this, I guess let's take a look. If the loop test is done at the end of the body for this branch, it's a simple branch, the corresponding branch will execute the pattern 1, 1, 1, 0 to the n, where 1 and 0 represent taken and not taken respectively, and n is the number of times the loop is executed. Clearly, if we knew the direction this branch had gone on the previous 3 executions, then we could always be able to predict the next branch direction. Simple. Basically, it's a pattern. But it's a very simple pattern. We're not trying to detect very complex patterns. If you see 1, 1, 1, 0, the next time you'd better predict 1, right? Because this branch always repeats 1, 1, 1, 0. And if you see 1, 1, 1, 0, 1, 1, you again predict 1. If you see 1, 1, 1, 0, 1, 1, 1, 1, you predict 0. Okay? So how do you capture this? In a similar way. Instead of having a global history, now we're going to have a per branch history register. For each branch, we're going to have a history register that records what was the outcome of the branch the last n times that branch was executed. And we're going to take that history of that particular branch and see what was actually basically indexed into this pattern history table and get the prediction per branch history. It's called the local history or local branch predictor. Again, this uses 2 levels of history. I guess let's try to do this. This probably will not work. I want to show you both over here, but instead of having a single register that's global, now we have a bunch of history registers, one for each branch. And based on the program counter, we pick one of the history registers. This tells us what was the execution history of that particular branch the last n times it was executed. And we're going to use that to index into a pattern history table that basically tells us what was the outcome of that branch last time we saw that particular execution history. Level 1, level 2. Except level 1 is now local history for that particular branch. Okay? So if you look at this, it's exactly the same thing I drew here. I think I don't have anything else to add here. Okay, if you look at this, now instead of having a single global history register, as in the global predictor, we're going to use a program counter and get the history, and that history for that program counter will be used to index the direction predictor. And there have been many, many different variations of this, but this is the basic idea. Now you can exploit this local history. Okay. Actually, it turns out that neither of these are the best. Some branches are good to predict, easier to predict with global history because they're correlated with other branches. And some branches are easier to predict with local history because they're actually correlated with themselves, with their previous executions. They have some patterns. So that's the idea of hybrid branch predictors. Can we combine the two ideas? And the answer is, of course, yes. Basically, now we're going to use more than one type of predictor, multiple different algorithms. Think of this as an algorithm for prediction. Think of this as another algorithm for prediction. And we're going to do multiple predictions, but select the best one. For example, we can have a hybrid of 2-bit counters, one level of history, and a global predictor. We can have a hybrid of this local predictor and a global predictor. We can have a hybrid of 3, local predictor, global predictor, 2-bit counters. That sounds more like some of the Intel branch predictors today. So what are the advantages? You get better accuracy because different predictors are better for different branches. And you get another advantage, actually. You get reduced warm-up time. Some predictors take very long to warm up. Because if you look at this, you'd better see that history for that branch enough number of times to gain some good prediction here, right? Whereas if you think of the last time predictor, you don't need much history, right? You warm up quickly because you've seen the last time, just last time it was executed. But here, if you want to fill up these different histories for that particular branch, let's say this is a 16-bit register, how many different values are there for that 16-bit register? Lots, right? Maybe that branch doesn't see all of those histories, of course, but it takes time to warm this up. So if you have multiple different branch predictors, you can use a fast predictor while this other predictor is not warmed up yet. Disadvantages? Well, I guess one disadvantage is how do you select? How do you do the selection nicely? How do you know which one's better? And here that confidence estimator actually comes in that you mentioned. Maybe for each predictor you have a confidence saying this predictor is doing well for this branch and this predictor is not doing well for that other branch. And people have used something like that also. I'll give you an example from alpha 21 to 64. If you have any questions, you can ask Dr. Kessler after his talk. Okay, so you need a meta predictor basically that selects between different prediction mechanisms. What is the downside of this? Well, you get longer access latency, and I'll show you the structure. So these are actually implemented in alpha 21 to 64. This is called the tournament predictor in alpha 21 to 64. And this is the paper I mentioned earlier. If you look at this, well, a little bit about the processor. They had a minimum branch penalty of 7 cycles. And typical branch penalty of 11 plus cycles. This is based on the profiling of their programs. It's an out-of-order execution machine. So typically, a branch resolves in 11 cycles. It was a 4-wide machine, which means that you waste 44 instruction slots if you get a branch misprediction. So it was important for them to minimize the branch misprediction rate. So they did target prediction with target address stored in the iCache, and you can read the rest. But if you look at this, the predictor is a global-local hybrid. Let's take a look at the global predictor. It's exactly as what I described to you, right? It has a global history, 12-bit global history register, like that. And you would use that to index into a 2-bit table of 2-bit counters. That's basically it. Now, if you look at the local predictor, it had 10-bit local history register here. And you would use a program counter to index that. You would get those 10 bits and you would index into a pattern history table. And it turned out that they actually put 3 bits per entry in that pattern history table because they didn't want that much they wanted a lot of hysteresis, apparently, for that. Now you have a local prediction here and a global prediction here. How do you select between them? This was their selector. They took the global history, and that global history register indexed into a choice predictor that said, the last time I saw this history, which predictor gave me the correct prediction? So it's all dynamic. So if a predictor consistently gives a good prediction, this choice predictor would be biased. It's again a state machine for 2-bit counters. This choice predictor says, the last time I saw this history, I strongly believe that this local predictor is going to give me the correct prediction. Right. And you could change that behavior, of course. If you keep getting wrong predictions from the local predictor, now you start believing that your global predictor is going to give you more information. So that's how it works. This is a real design. And in fact, there are other real designs that take another input with some other predictor over here. In fact, alpha was not this simple. There were other predictors inside. If you read this paper, you will see that they had other simple predictors. Because these take long to warm up. So what happens if these are not providing good information to you because they're not warmed up? Well, a bimodal predictor is very good for that, right? Bimodal predictor is a 2-bit counter predictor. So instead of using any kind of second level of history, you just use the program counter, access the BTB, and the BTB tells you the last time you saw this branch, it was taken or not taken. Or the last n times you saw this branch, it was taken or not taken. That's very quick to get. And alpha actually used that in a different way. They called it line prediction. We're not going to get into that, but the same idea. If these predictors are not providing you good information, have another input here that provides you information that's better, potentially, or that's faster to get. Okay? So many out-of-order execution engines that you have today employ even more sophisticated predictors than this. And now you know the fundamental principles based on that. They may look a little bit different, but they all employ this history-based prediction. So what is the benefit of this? And this is a very old slide, actually, from old benchmarks. This is on the x-axis, we see the conditional branch prediction accuracy. On the y-axis, we have these old benchmarks that people still use today. Amazing, right? GCC people use today, right? And some NASA applications apparently. SPICE simulations if you do that. I think this is spec 92, if I'm correct. This is from the McFarling paper. And this gives you the prediction accuracy for 3 different kinds of predictors. Bimodal predictor, which you probably cannot see because I cannot see, which is the 2-bit counter predictor, the G-share predictor, and a hybrid of bimodal and G-share, not even a local plus G-share. If you look at this, the branch prediction accuracy improves significantly from bimodal to G-share. And it does improve significantly. This is the average. I guess you only need to see the average. For bimodal, for these benchmarks, I guess you're lucky here. Bimodal, you get 91% accuracy. For G-share, you get 93% accuracy. And for bimodal G-share combination, you get almost 96% accuracy. And if you look at this EQNTOTT application, once you go from local, I guess local branch prediction somewhere around here, if you can imagine. Once you go to G-share, the prediction accuracy goes to 91%. So that global correlation, exploiting that global correlation gets you a significant prediction accuracy. But these are old benchmarks. The results are similar across a wide variety of benchmarks if you look today. Okay, I think before we conclude, let's talk about biased branches. People have observed that many branches are actually biased in one direction. For example, many branches are taken 99% of the time. The problem is if you actually have one type of predictor, these branches pollute the branch prediction structures. Because most of the time you know that this branch is taken or not taken. But if you're using the same branch prediction structure for that particular branch, these branches interfere with other branches' predictions because you're updating the same counters that are shared by other branches. So if you look at the global history register here, it's used for all branches, right? Regardless of whether or not the branch is always taken or always not taken. And these always taken and always not taken branches update the same history structures, same prediction structures with those branches that are much, much harder to predict. So people have observed this, and people have said, why do we actually update the branch prediction structures with these biased branches? If we detect a branch is very, very biased, let's predict it as always taken or always not taken somehow with some information. Maybe the compiler provides that information. But I'll leave it up to you to figure out how to detect such biased branches. That could happen actually if you have a good choice predictor also. Maybe somehow you figure out the branch is biased and you never update these tables for that branch. But that's the idea. Detect such biased branches and predict them with a simpler predictor. And a lot of existing branch predictors employ this. You could think of this as a filtering mechanism. Filtering mechanism that doesn't update most of your branch prediction structures for these biased branches. And this is the paper that actually introduced that idea. It's called branch classification. You can classify branches based on their predictability and use different predictors for that purpose. Okay, I think I'll stop here. We've covered most of branch prediction, but we're going to cover more control dependence in the next lecture, and then we'll jump into exceptions, interrupts, and out-of-order execution. I'll see you Wednesday. Don't forget your lab.